Let's kick things off with the big question. Why are scientists so urgently searching for new antibiotics? I mean, we still have penicillin and all those classic drugs, right?
It's actually a bit alarming. Many bacteria have become resistant to those old favorites. Pathogens are evolving faster than our drug pipeline, and the number of newly approved antibiotics has dropped off dramatically over the past couple decades.
That sounds like a real crisis. I read somewhere that most antibiotics we use today come from natural sources, especially bacteria. Is that true?
Absolutely. And it's wild to think about. Over 90% of clinical antibiotics originate from microorganisms, not just plants or animals. The golden era of antibiotic discovery, from the 1,940 seconds to the 1,970 seconds, saw tens of millions of soil microbes screened. But now, many easy to find compounds have already been picked up.
So, we've already harvested the low hanging fruit, but bacteria keep outsmarting us. That actually makes me wonder, what strategies are researchers using to look for the next big thing in antibiotics?
Funny you ask, because antibiotic discovery has evolved through a few main approaches. Historically, folks would just screen natural extracts for activity, sort of a trial and error, looking for anything that killed bacteria, even if they didn't know how it worked.
That's the classic let's see what happens method, right? Just growing stuff from soil and testing it on bacteria. But nowadays, is it more targeted?
Exactly. There are two newer strategies. Chemical screening, where researchers hunt for new chemical structures regardless of their initial activity, and target-oriented screening, where they go after compounds that hit specific molecular targets in bacteria.
Target oriented sounds high tech, but I imagine it's not that simple. Drug targets have to be present in bacteria, but not in humans, and resistance is still an issue, right?
You've nailed it. Picking a good target is tricky. And even with all three strategies, there's a major headache. Rediscovering the same old compounds over and over. That's why scientists have started trying some pretty creative new techniques.
Let's talk about those creative approaches. I heard that most bacteria on Earth have never even been grown in the lab. Is that where researchers are looking now?
Exactly. And it's actually kind of mind-blowing. Less than 1% of actinobacteria, which are famous for making antibiotics, have ever been cultivated. Scientists are now using advanced cultivation tools, like microfluidic bioreactors, to grow the unculturable one.
Microfluidic bioreactors almost sound like tiny science fiction factories. What happens once they manage to grow these elusive microbes?
They can screen them for new compounds, and some huge discoveries have already come out of this. Like Taxobactin, a new antibiotic from a bacterium previously thought impossible to study. Plus, new habitats like deep sea or even our own noses are being explored for novel drug producers.
That's wild. It makes me think beyond just growing new bugs, isn't DNA sequencing opening up even more doors for finding antibiotics? I keep hearing about genome mining.
Oh, genome mining is a total game changer. Instead of searching for molecules, researchers look directly at bacterial DNA to find gene clusters that encode for new compounds, even if those compounds haven't been made in the lab yet.
So, it's like reading the instruction manual before you even see the product. That must save a ton of time and lets you hunt for much more chemical diversity.
That's a great way to put it. Tools like anti-smash or PRISM can scan entire genomes quickly, flagging clusters that might make antibiotics. And some methods even look for clusters with built-in resistance genes, since bacteria have to protect themselves from their own weapons.
But if the genes are there, why don't we see all those compounds in a petri dish? Are there secrets to turning on these hidden biosynthetic factories?
Exactly, many gene clusters are silent under lab conditions. Scientists engineer bacteria, change their environment, or swap out genetic switches to activate those clusters. It's a bit like finding a locked room full of treasure and finally getting the key.
So, say you found a promising new molecule, how do you know it's really new? Not just another version of penicillin in disguise.
That's where dereplication comes in. Scientists use advanced mass spectrometry and bioinformatics to compare new compounds against huge databases. It's sort of like running a fingerprint scan before getting too excited.
That's a relief. You'd hate to spend years chasing something already sitting in your medicine cabinet. But it doesn't stop there, right? What strategies are on the horizon for making these discoveries useful and fighting resistance?
You're spot on. Beyond finding new antibiotics, there are clever twists like antivirulence, which don't kill bacteria but just block their harmful actions, or combining drugs to make resistance tougher. There's even research into making antibiotics sneak into bacteria disguised as nutrients, like a Trojan horse.
It feels like a mix of detective work and creative engineering. But despite all these advances, there have to be some big hurdles left to clear, right?
Definitely. Even with all these new tools, genome mining, clever cultivation, genetic engineering, there are serious scientific and economic hurdles. Many potential drugs never make it to the clinic, often because of side effects or tricky regulations.
And with resistance always waiting in the wings, we can't just find a new drug and relax. I imagine the push now is for smarter prescription practices and tighter controls, especially in both human and animal health.
Exactly. Plus, the industry needs to support not only broad spectrum miracle drugs, but also those targeting specific pathogens. Thankfully, regulatory agencies are streamlining approval for promising new antibiotics. So there's hope we'll see more options soon.
So, it sounds like we're entering a new age of antibiotic discovery. But innovation alone won't be enough. We'll need collaboration, better management, and maybe a bit of luck too.
You summed it up perfectly. With global cooperation and these cutting-edge techniques, there's real hope we can keep the upper hand in the battle against bacterial infections.